Hey everybody, in this video we're going to be practicing related rates. Specifically, we're going to deal with 4 problems that deal only with area. If you're looking for related rates problems with other concepts, please look out and check for the other videos in this playlist. If you want to follow along, the links to the companion worksheet are in the description below, so let's get started. So for this first one, we're given the length of a rectangle is decreasing at the rate of 3 inches per second, and the width is increasing at the rate of 4 inches per second. And when the length is 15 inches and the width is 4 inches, find the rate of change of the area. So the first thing we start with is what formula relates the length, the width, and the area. That's what you always start with when you have related rates, is what connects those 3 things. Since it's a rectangle, the area is going to equal the length times the width. Now in this problem, all 3 are changing. The length is changing, the width is changing, and the area is changing. So when we talk about related rates, we're not going to leave these as a constant. We're going to leave them as variables. So when we take the derivative of A is dA dt, because remember, it's according to time, not according to length or to width. Now length and width are 2 quantities that are being multiplied, so we have to use product rule. So we have dl dt times, and we leave w alone, plus, and then we leave l alone, times dw dt. And so we want to know when the length is 15 inches and when the width is 4 inches. So that means we're going to put 15 in for w and 4 in for l. 15 in for l. That's 15 over here. And 4 in for w. Now dl dt, the length of the rectangle is decreasing at the rate of 3 inches per second. So that rate is -3. Negative because it's decreasing. The width is increasing at the rate of 4 inches per second. So that means because it's increasing, the rate is a positive. So we have -12 plus 15 times 4 is 60. So when we add these, we get 48. Now it's always important that when you have a problem like this, that you stay consistent with the unit. Now this is a unit of area, so that means it's going to be square inches per second, because seconds is our unit of time. So let's look at the next one. For the next one, we have the area of an equilateral triangle is increasing at the rate of 5 square millimeters per second. We want to find the rate at which the height is changing when the area is that amount. Okay, so we need a little more information here in order to solve this. So we have an equilateral triangle, and all the sides are equal. They all have a side length of x. But as we know, the common area formula that we use to find the area of any triangle is 1/2 the base times the height. So if one side is x, that means that's the length of the base. What about the height? That's the question. Well, the thing to keep in mind is that in an equilateral triangle, if we draw down the height, that makes a right angle. And so we've got a little right triangle here. And we know that because all the sides are equal, the angles are equal also. So this angle is 60 degrees, which means this is 30 degrees. So if I cover this up, I can just treat the half of this equilateral triangle like a 30, 60, 90 right triangle. And so if x is my hypotenuse, then down here I have x over 2 as my short leg. And so the height is square root of 3 times this length. So this length right here is going to be x times the square root of 3 all over 2. So if I plug those values in to the area formula, I have 1/2. The base is x times the height, which is this quantity right here. X square root of 3 over 2. If I combine the denominators, this is over 4. On the top, we have x squared, and then we still have the square root of 3. Now you will see some people write it this way, What you will also see is you will see some people write it as the x squared separate from all the numbers. And so it will be written as square root of 3 over 4, like that. Okay, so now what we want to do is we want to say, well, if this is what the area equals, what should be the length at that time? Because here's what we have. We're given that the area is 64 over radical 3. So we have square root of 3 over 4 times x squared. So if we multiply both sides by square root of 3, that will eliminate this denominator. So we have 64 equals 3/4 times x squared. If we multiply that by 4, we will get 256 equals 3x squared. And then we can divide by 3, but since 256 is purely a power of 2, that's not going to reduce at all. So we have 256 over 3 equals x squared. And so we have the square root of 256 over 3 equals x. And if we take the square root of 256, we get 16 over radical 3. That equals our side length. Now actually we haven't done any related rates yet, because all we've done is found out what is the length of the side, that is, down here, 16 over radical 3, when the area is 64 over radical 3. Now we have to go back and say, well, wait a minute. Let's go look at our formula and let's apply some related rates. So if this is our area formula, square root of 3 over 4, then our related rates, dA dt, equals square root of 3 over 4 is going to be a coefficient times 2x. That's the derivative of x squared. So we have, and also dx dt, because x changes according to time. So we have square root of 3 over 2x times dx dt. Now what do we know? Well, we know the length of the side. That's what we found. We want to know at what rate the height is changing. Okay, we can find that. Now dx dt is the rate at which any side length of x. So the height's going to be a little different, but not by much. Now we know what the rate is. The rate is growing at the rate of 5 millimeters squared per minute. So we put 5 in for dA dt. We put 16 over square root of 3 in for x, and dx dt is what we're solving for. Now the square root of 3's, they cancel, and we have 16 over 2. That will simplify to just 8 times dx dt. And so when we solve for dx dt, we get 5 over 8 millimeters per minute. And that's the rate the side lengths change. But what we want is, we want to know how fast is the height changing. And so up here, the height is x times square root of 3 over 2. So what we have to do is we have to say, well, the height is the quantity square root of 3 over 2 x. And so the rate of change of the height is going to be that derivative. So if we find the derivative of this, this is just square root of 3 over 2 times dx dt. Well, we know what dx dt is. dx dt is the 5/8 that we found. So we have square root of 3 over 2 times 5/8 eighths. So we have 5 square root of 3 over 16 millimeters per minute. And this is the rate at which the height of the triangle is changing. Right, let's move on to the next one. So with the next one, now we're dealing with a circle. And so it says the radius of a circle is increasing at a constant rate of 0.2 meters per minute. In terms of the circumference, what is the rate of change of the area of the circle in square meters per minute? So we want to know rate of change of the area of the circle given the radius. So we need to relate these two quantities. So the area of a circle is pi r squared. We can take this derivative with respect to time. So dA dt equals pi times 2r times dr dt. Now, what do we know? We know that the radius is increasing at a constant rate of 0.2. So we can plug 0.2 in for dr dt. I'll put the 2 out front times 0.2. Now, what's interesting is it says it wants this in terms of the circumference. Now, right now, it's in terms of the radius because the radius is the variable. But it wants it in terms of the circumference. So we need to replace that somehow with what the circumference is equal to. But if we recall, circumference is equal to 2 pi r. It's equal to that expression. So we can just take out this whole expression and replace it with c, the circumference, times 0.2. And so there is the change in area in relation to the circumference. Whatever the circumference is, you just multiply it by 0.2, and that is how fast the area is changing. All right, so looking at the final one, it says a leaking oil tanker causes an oil slick on the ocean. When its radius is 150 feet, the radius is expanding by 0.1 feet per minute, and its thickness is 0.2 feet tall. At that moment, how fast is the area of the slick expanding? Now, some people would look at this and say that, well, if you're talking about an oil slick and it has a thickness, that means you're talking about volume. And so this is the wrong video for that. Well, actually, not necessarily so. And that's because the thickness or the height isn't changing. The thickness is 0.02 feet. It's the area that's expanding. So we know that the radius is expanding by 0.1 feet per minute. Its thickness is expanding by that. But since the thickness isn't changing, all we're really worried about is the surface of the slick. And it's a circle. And so this takes us back to area equals pi r squared. And so since we want the change in area, we take dA dt equals 2 pi times r times dr dt. And in this case, r is going to have a value of 150 feet, and dr dt is 0.1 feet per minute. So all we have to do is multiply 2 times 150 times 0.1, and that gives us an answer of 30 pi. Now our unit is square feet, so square feet per minute. And if you want an approximate answer, that's going to be approximately 94.248 square feet per minute. Now, all of these, again, are just area-related rates problems. So be looking in the playlist if you're looking for a different type of related rate problem. If you like the video, please give a thumbs up. For more videos like this, click the subscribe button. If you're a teacher and you like this, consider sharing it with your students. If you're a student and you like this, please share it with your classmates. If you have suggestions or other problems that you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching. And remember, the only way to understand something is to do it.